Okay, so in this last video, I'm going to take the renal handling of acid-base, which we've talked about in detail now in the first two videos, and I'm going to try to fit it into the big picture of body handling of acid-base. Okay, we're not going to go into tremendous detail here. We're saving that for the actual acid-base section, but nevertheless, I think I can put the kidney's role in this into context without going into too much detail. Okay, so when we talk about the kidney, what we're really talking about is handling of bicarb, right? The net body gain or loss of bicarb is equal to new bicarb gained in the plasma minus the bicarb lost in the urine, okay? So you get new bicarb when you have proton binding to phosphate, or primary titratable acid, and ammonium in the urine, okay? So when that happens, you excrete protons and you form a bicarb. So when we talk about getting rid of 60 milliequivalents per day of acid that you take in through the diet and you generate through metabolism, or where you lose bicarb in the feces, as we talked about in the first video. When we talk about getting rid of 60 milliequivalents per day of acid, we're talking about gaining 60 milliequivalents per day of bicarb, okay? So we're in balance when you gain 60 milliequivalents per day of bicarb as you excrete protons, okay? So let's take a look at how this works. If you're at normal pH, a normal person, pH 7.4 plasma pH 7.4, you typically reabsorb virtually all of the bicarbonate. You might, lose a little bit. I've got a -1 here where you lose a little bit of bicarb in the urine, but for the most part, you reabsorb everything, as I said in the first video, okay? So you're losing a bicarb here, but notice that as we excrete acid bound to titratable, in the form of titratable acids like phosphate, or urine ammonium, which is non-titratable, as you excrete those acids, you gain bicarb. So you gained 61 here, you lost 1 here. The net gain of bicarb is plus 60. So you're in balance. You've excreted 60 milliequivalents of hydrogen ions, and you gain 60 milliequivalents of bicarb. Your body is in balance, okay? At pH 7.4, when you gain 60 bicarb to offset the 60 milliequivalents per day of acid that you've generated or taken in, all right? Okay, so that's normal. Your normal urine pH, about 6, all right? Now let's talk a little bit about alkalosis. So now, if you have an alkalosis, you have too much bicarb, all right? If we look at our Henderson-Hasselbalch equation, you have bicarb concentration in that numerator. So one way or the other, the ratio of bicarb to carbon dioxide is going to be greater than 20, and the way that your kidneys compensate for that is by dumping bicarb so you can get that ratio back down. So now, instead of our urine bicarb losing just a little bit of bicarb, now you're actually losing a lot of bicarb through less reabsorption and through bicarb excretion, okay? You've got practically no loss of hydrogen ions through titratable acids or ammonium. So now our net is minus 80, where we've actually lost bicarb from the body, and that's pretty much what we want. We want to bring the bicarb down so we can bring the pH back down as well to 7.4, okay? And now our urine pH is about 80. During acidosis, now we have an excess of hydrogen ions. So now, again, we continue to reabsorb urine, bicarb. Here we lost a little bit, now we don't even lose that, all right? And now we are generating new bicarb for the body by excreting acid, titratable acids, primarily phosphate, and ammonium. And here we have it, 40 and 160, all right? And so we have a net gain of bicarb of 200. So now if we think of our Henderson-Hasselbalch equation, what this does is it brings the numerator up. And so during acidosis, our ratio of bicarb to carbon dioxide less than 20. So one way to restore that balance is to increase the bicarb. This increases the bicarb in the body. This brings your pH back up toward normal 7.4, okay? And so now our urine pH is pretty acidotic because we've got a whole bunch of hydrogen ions being excreted. Do note that the vast majority of this compensation is through ammonium generation from ammonia here, okay? Now I know in a previous video I told you that during acidosis you can form phosphate in the body. That phosphate is filtered and that can help with binding the acid, and so you'll excrete more acid through phosphate. That is true, but it doesn't contribute all that much. Ordinarily what happens is you increase the amount of hydrogen ion bound to ammonia to form ammonium, and that makes up the vast majority of this increase in new bicarb that you've got in the body here that is going to bring your pH back up, okay? So that's what's happening here, all right? All right, so let's talk about acid-base disturbances now in terms of what we just said with the kidneys handling of bicarb and acid. So overall, the acid base in the body is controlled through this equation, arguably the most important chemical equation in the body. Okay. You have CO2 on this end, which your respiration controls. So if I breathe really fast, I blow off CO2, get rid of CO2 at a higher rate, my plasma CO2 drops. Okay, my partial pressure of CO2 drops. Okay. If I breathe more slowly, then my partial pressure of CO2 rises because I'm not getting rid of as much. On the other hand, we have bicarb here, which your kidney controls. Okay. If you have acidosis, then your kidney is going to generate a bunch of new bicarb. Okay. If you have alkalosis, then your kidney is going to dump bicarb. Okay. All right. Through the mechanisms we just talked about in the previous videos. All right. So general categories of acidosis and alkalosis. We have respiratory acidosis and respiratory alkalosis. This is where you have too much carbon dioxide because of a respiratory disease. This is where you have too little carbon dioxide because of a respiratory disease. Let's say you're breathing too fast, you have some sort of a panic attack or something like that. Okay. Metabolic acidosis is where you have too little bicarb, okay, through something like, let's say, diarrhea, where you lose bicarb at a higher than normal rate, or metabolic alkalosis, where you have too much bicarb, maybe because you're losing acid through vomiting, through loss of hydrochloric acid in the stomach, okay? Okay. So again, the important equation to remember here, the Henderson-Hasselbalch equation. And again, if it's normal pH, the ratio between the bicarb and 0.03 times partial pressure of CO2 is 20. If that ratio is higher than 20, then you have an alkalosis on your hands. If it is lower than 20, you have an acidosis on your hands. All right? And again, plasma pH depends upon both of these values because either one or both could affect that ratio. All right. So a normal person has a ratio of bicarb to 0.03 times CO2 of 20, right? And that's what we have here. To make things simple, we call the bicarb 20. To make things simple, we call it 0.03 times CO2, which is what this really is. We call it 1, right? Just to make it simple. The ratio 20 to 1. The ratio is 20. Remember that, all right? That's normal. CO2 1, bicarb 20, ratio 20, pH 7.4. All right? Now, let's talk about our acid-base disorders, and now let's talk about respiratory acidosis. All right, so now our normal carbon dioxide 1 becomes 2. It's because of a respiratory problem. Let's say you have COPD, emphysema, something like that, that causes you to be getting rid of less carbon dioxide. The carbon dioxide builds in the plasma. So we have higher than normal carbon dioxide. Now our ratio in our Henderson-Hasselbalch equation is 10. Less than 20, that means acidosis, and if you actually do this calculation, you get a pH of 7.1, respiratory acidosis, right? And that's what we have here, a ratio of 10, all right? So how does your body compensate for respiratory acidosis? Well, it's going to have a hard time compensating through altering respiration because it's the respiration that's messed up, okay? So what you're going to typically do is you're going to compensate by adding bicarb to get your ratio back to 20 to 1. So this is where your kidneys come in, where your kidneys actually add new bicarb in the face of an acidosis. So now we still have a CO2 of 2, which is high, but now because we've generated a bunch of new bicarb in the kidney, we have 40 bicarb instead of 20 here. The ratio is back to 20 to 1, all right? Which means we have a normal pH again of 7.4, all right? So this is our disorder, respiratory acidosis. This is how your body compensates by generating new bicarb with kidneys, okay? So, and that's the same as so now let's talk about respiratory alkalosis. Now this is a case where you're getting rid of too much CO2. Let's say you have a panic attack or something like that. You're breathing too rapidly, you blow off a bunch of CO2. The CO2 drops from 1 to 0.05, the CO2 part of our equation, okay? So now, once again, we have 20 bicarb. Now it's 0.05 CO2. Our ratio is 40 here. That's greater than 20. That means our pH is higher than normal. All right? We have a respiratory alkalosis. All right? How does your body react? Well, again, it's a respiratory problem. You're going to have a hard time compensating for this through respiratory mechanisms. So you compensate through a renal mechanism, okay? And in this case, you dump bicarb. These white squares mean bicarb that was there that's gone now, okay? So now our bicarb has gone from 20 to 10, okay? And the ratio of 10 to 0.5 is 20. Our ratio is back to 20 in our Henderson-Hasselbalch equation. If you do the calculation, you have a pH of 7.4, all right? So now we can talk about the metabolic acid-base disturbances and compensation. So here we have metabolic acidosis. This would be a disease where you would lose bicarb. Typically it might be through something like diarrhea or something like that. That's the classic one, right? So the normal bicarb on our last slide was 20. We've dropped to 10. So now our ratio is 10, which is less than 20, and sure enough, our pH is less than 7.4. Okay. So the way that your body compensates for that, this time it's twofold. Now we have compensation by increasing our rate of breathing, which drops our carbon dioxide from 1 to 0.75, and at the same time we'll have a renal compensation, which will bring our bicarb from 10 to 15, so we'll actually be gaining bicarb. At the same time, we're slowing our respiration, so now we're changing both numbers, okay? And so we've gone from a ratio of 10 to a ratio of 20 here by compensating through both mechanisms, and that gives us our normal pH of 7.4, okay? Note that this scenario assumes that the metabolic disturbance is not of renal origin, it is of non-renal origin. If it's a problem with your kidneys, then your kidneys are going to have a hard time compensating. So here we're assuming that it's non-renal origin, but you should recognize the fact that there are acid-base problems of renal origin that you may have to deal with, and these are going to be very limited in terms of what they can do on this side of the equation, okay? All right. So having said that, let's talk about metabolic acidosis. And again, we're going to assume this is non-renal. So somehow now we'll talk about metabolic alkalosis, excuse me. So somehow you have gained bicarb, and this is typically indirectly. Let's say by vomiting a whole bunch of hydrochloric acid and losing it from the stomach, that will result in you gaining a whole bunch of bicarb in the body because you've lost acid. So you end up with a normal, instead of a normal 20, you end up with 40. Our CO2 is a normal 1, and our ratio is 40 here, all right? And that's a higher than normal pH, all right? So now we compensate, and again our compensation is twofold, assuming that this is non-renal. We slow our respiration, so our carbon dioxide goes from 1 to 1.25, and our plasma gains carbon dioxide. At the same time, we dump some bicarb, okay? And so our bicarb goes from 40 to about 25 here. You can't see that, that's 25. And if you calculate the ratio, after compensating through both the lungs and the kidney, you have a ratio again of 20 and a normal pH of 7.4, all right? So once again, bear in mind that there is such a thing as renal origin, metabolic disturbances of renal origin, and when the kidney is the problem, then you're going to have a hard time adjusting to that problem through the kidneys handling of bicarb or hydrogen ions. Because the kidney is what's messed up, it's what's causing the problem, okay? So bear in mind that the renal compensation is going to be limited in this case, all right? On the other hand, it will play a role in this case. And you should also bear in mind when we talk about these mechanisms that the renal mechanism is typically really slow over a period of hours to days, whereas your respiratory compensation is almost immediate, right? I mean, that happens really quickly. You can adjust your breathing rate pretty quick, okay? So you're talking about seconds to minutes there, all right? Seconds to minutes to hours, all right? Finally, let's talk about the anion gap a little bit. So ordinarily in your body, really under all circumstances, wherever you have cations, those have to be balanced by anions. And in your body, that is true, okay? The concentration of cations is equal to the concentration of anions. It must be true, okay? The two have to cancel out. So why would you have what we call an anion gap? Well, this results from this equation where we take the primary cation in the plasma, sodium, and we subtract the concentrations of the two primary anions. When you take the cation, the sodium concentration, you subtract this sum, what you get is 14. So this 14 is what we call the anion gap. And so the first thing to recognize is this is an apparent gap, okay? It's not a real gap. There is no anion gap in your body in reality, okay? What this is the concentration of anions that are not chloride and bicarb that would be needed to compensate for the that are helping to compensate for the sodium concentration, okay? These anions exist. It's not a real gap. It's just that they exist in a form other than chloride and bicarb. So this is a typical normal anion gap, about 14. So what does this have to do with acid-base? Well, if I add acid to the body, okay, then as I've sort of tried to pound home, if that's coupled to an anion other than chloride, okay, so this hydrochloric acid, it doesn't work, but for the others it does. Let's say it's lactic acid, okay. So when you add protons to the body, let's say in the form of lactic acid, bicarb disappears, okay. Whenever you add fixed acid, bicarb goes away, all right? So what that does is it increases this number because this number goes down. Now that doesn't mean that we haven't added anions to make up for the loss of bicarb. We have. If it's lactic acid, we've added lactate to the body, but lactate's not in this equation, okay? Bicarb is, so when it drops, this gap goes up. So when you have a higher anion gap, it's a sign that maybe you've got an acidosis on your hands, okay? Because acid's been added to the body and bicarb has disappeared. all right? And that's something to bear in mind when we talk about acid-base problems. The anion gap can give you an idea that a problem might exist. And again, it's indicative in the case of acidosis of the loss of bicarb from this equation, all right? All right, that's all I've got. We'll handle the details on acid-base when the acid-base, during the acid-base section, but for now we'll cut it off here and I'll see you guys in the rooms.